So first of all, I want to thank the organizers of this summer school for this kind invitation. Due to this invitation, I got the chance to visit Iceland for the first time in my life, and it was already completely worth it, I think. Here I want to talk in this presentation about the importance of cognitive mechanisms in AGI systems. And before we start with the content, first of all, some propaganda. This is some information concerning cognitive science and the cognitive science programs in Osnabrück. Osnabrück is a little city in the northern parts of Germany, and here are some features of these things. So we have currently, for example, 11 professorships, and we cover a broad range of different disciplines. So, for example, philosophy of mind, cognitive psychology, neurobiopsychology, artificial intelligence, computer vision and neuroinformatics, and some more. We have 3 programs. There's a cognitive science bachelor's program, a cognitive science master's program, and a cognitive science PhD program. We have currently around 130 freshmen in the bachelor's program, around 30 to 40 new master students per year, and the PhD program completely has more than 30 enrolled PhD students. It's a very interdisciplinary field, a very interdisciplinary institute, and a very inspiring atmosphere, in my opinion. Okay, now here's the overview of this presentation. I think, coming back to our discussion before, this is also, at least at the beginning, a very colorful and visual presentation. So I start with some examples of the breadth of human general intelligence, how I called it. So remarkable abilities of humans to solve problems, to recognize things and stuff like that. We will see that. Then there are some classical types of reasoning and learning. There will be 2 little tables about that. And then my claim is essentially that all these classical forms of reasoning and learning, and again I try to be as provocative as possible to generate a discussion somehow, are not able to model these things humans show in the examples. And then we will talk a little bit about analogy making in a framework we developed in Osnabrück, so-called heuristic-driven theory projection, and concept blending. And at the end I want just to speculate about future applications of analogy making, concept blending, and probably some more cognitive abilities in domains such diverse as the semantic web, or text understanding systems, or mobile control systems for heating systems, for example, in households and stuff like that. And then I will have some conclusions. Okay, now let us start with the remarkable breadth of human general intelligence. By the way, as usual, I have probably too many slides. If it's necessary, I perhaps skip some of them. Now, first of all, I want to make an experiment with you. On the next slide, there will be some axioms, so some formulas, logical formulas, and you can have a look on them, and then you tell me what they mean, okay? And hopefully nobody comes up with a solution. That's the idea of the whole thing. So if you know them already, then, well, okay, then it's bad luck for me. So these are the axioms. And the question is, what do they mean? What's the semantics of these axioms? So for example, you have a predicate C, and for every x, x holds, for example. There's a predicate C that is also not only reflexive in a certain sense, but it's also symmetric. So if Cxy, then Cyx holds. Then there's a defined predicate P. So if Pxy, then this is the case if and only if for every Z, Czx implies Czy, and so on and so on. Any ideas what that could mean? Good. you shouldn't be able to give them a meaning, actually. That is just cognitively, shouldn't be cognitively possible. Right? Okay, now I give you a little bit semantics, what they mean, and then you should have an idea, right? That's on the next slide. I write just as kind of an explanation to every axiom. So for example, there was this defined predicate P that is true if and only between x and y, which is true if and only if zx implies zy. And it should define a kind of a part-of relation between regions. Okay? So x is a part of y if and only if, for every z, and now z means connectedness, if z is connected with x, then z should be also connected with y, because one is contained in the other, and if there's a connection to the inner one, then it must be also connected to the bigger one. Okay? Seems to be plausible, right? Or something is disconnected if it's not connected. Or something is externally connected if it's connected but does not overlap. Overlap is like an intersection of two sets, intuitively, right? A partial overlap is an overlap where x is not a part of y and y is not a part of x. They are equal if both are parts of each other, and so on and so on. I hope now you get a little bit idea what's going on. Now, as a third step, I give you pictures. And then it should be everything should be trivial, hopefully, concerning these predicates. If you see these pictures, DCXX, like x and y is disconnected, EC for externally connected, PO for partial overlap, EQ for equality, and you have these intended models of these spheres, or these circles that are somehow have some relations to each other, then I think for everybody it should be completely transparent what's going on here, right? So the point is, humans think in models usually, in such things, and not in formulas. They have extreme problems to interpret formulas. Here it's much easier. But they can flip around between these things. Actually, we saw this before in this nice GDL description of this game here. Because if you want to code something on this formal style, this is somehow this symbolic style, then you quite often refer to such little pictures and look, so what's going on here, right? And this is your model, your intended model. You want somehow to code in your formalism, or in this case in the code of the program. Right? And so we are having this ability to flip-flop around. Okay, here are some other examples. So here I can probably go a little bit faster. Poems, the interpretation of poems. It's a remarkable ability. If you are asked, give me a metaphorical relation between frog and cat, I'm pretty sure you will have problems, or an analogical relation. Because frog and cat has nothing to do with each other, right? Frog is something that appears in horror movies, and cat is something you have at home or so. So they do not really have structural commonalities. But if you read this poem by Carl Sandburg's, the frog comes on little cat feet. It sits looking over harbor and city on silent haunches and then moves on. Then suddenly you have a whole bunch of associations why these things are strongly related to each other. Right? A remarkable ability of human beings. Then these classical IQ puzzles, so-called Raven's progressive matrices. That's the official name of these things. We are able to solve these ones and much more complicated ones. So you detect the regularity between the rows and in the rows and in the columns, and then you need to figure out you can choose from different possibilities what's the right input for the last figure. And then something that is also extremely interesting are noun-noun compositor, or noun-noun compounds. We can, in German, this is a very good language for that. English is also very good in that, but usually you don't get these very long noun-noun compounds. You probably quite often use hyphens, but in this example I think you can write them really together without a hyphen. If you consider the concept of a house and the concept of a boat, you can build things like a houseboat and a boathouse, right? A houseboat is something where people live in, although it's not a house, but a boat that is somehow at the coast of a river, for example. And a boathouse is a house where boats are somehow stored for some time because there's a storm or something outside. They mean completely different things. We are very, very creative in building such compounds and give them a meaning. For a computational system, this is usually called concept blending, what's happening here. And this is usually a problem for computational systems to compute this. Now another little experiment. You see a picture now. It's an advertisement. And you tell me what that means. I hope it's not very perfect resolution here, but there's an advertisement. It's about a company which is called Jeep, produces cars, SUVs or so. Yeah, what's the meaning of that? In particular, what are these animals there on this branch of this tree? Right? Any ideas? Do they mean anything? Is it just nonsense? Is it just a kind of arbitrary, creative whatever without any meaning?
Well, I can see a lot of possible interpretations. One that comes to mind is that the products from Jeep are very colorful, like the parrots.
Ah, okay, yeah, good, yeah.
Parrots imitate anything and anyone, so either someone is imitating Jeep or Jeep is imitating someone.
Okay.
Or, use a Jeep to drive through that mess.
Right, that is definitely what is intended by the forest or the tropical forest, that Jeep produces cars that also operate here. But to get this, what is necessary, what the parrots mean? If you think this is a traffic situation, what is the meaning of the parrots? What? Traffic lights, yeah. Traffic lights, right. Traffic lights. This is just the American way of horizontally putting traffic lights on big crossings, for example. And to come up with such an interpretation, give me the computer program that we have hundreds of these things, by the way, of these advertisements. And even for humans, it's sometimes extremely hard to interpret them. But try to build an artificial system that can come up with such interpretations. That's a hard task. Here's another thing from design, usually for business processes. So in design processes, you have relatively general abstract principles quite often. So for example, a very famous one is this nested doll principle, the Matuschka principle, I think it is called. In German, it's this Babuschka principle, as far as I remember this. It's just nesting objects into each other, right? And this appears everywhere. It appears in engineering context, in computer science context, in food production context, perhaps nesting table, nesting bowls into each other in order to reduce the space you need in your cupboard. Even certain very abstract things like fractals or self-similar pictures can be reduced to this principle. And there is a whole bunch of these things that reappear over and over again, and they can be subsumed somehow under this general principle of the nested doll principle. Very creative thing of humans to come up with such solutions to problems in arbitrary domains and using just the same principle. And here's the last one. This goes back to a book called Where Mathematics Comes From Lakoff and Nunez. Lakoff is originally a cognitive linguist. And they made the proposal, or they asked themselves the question, so how is it possible that little children come up with the rudimentary number concepts of 1, 2, 3, the successor principle, and stuff like that? And clearly they don't learn axioms or piano arithmetic or so, but what they do, they know a lot about real-world actions. So, for example, they can, on the right bottom, motion along a path, they probably know to walk along a path, to stop, to go back to the origin and stuff like that. And steps are usually considered as a unit somehow, right? They have perhaps Lego bricks or something like this, and they play around and they build these little bricks and build something complex and they decompose it and stuff like that. That's the object construction metaphor here. And probably they collect things and they give something to the parents and they get something from the parents and collect a heap of, let's say again, Lego bricks or something else, little cars, toy cars or so. And this is the object collection metaphor. And the idea of these authors is that such real-world, grounded real-world actions in real-world situations somehow are the basis in order to abstract from them to a rudimentary number concept, 1, 2, 3, 4, without having clearly a full-blown arithmetic, clearly, but a kind of a rudimentary conceptualization. That one is bigger than something else because on my path I'm farther away from the origin than here, let's say, for example. Or one heap is bigger than another heap, then probably the number of the similar object should be bigger, and so on and so on. And usually what happens here, they call this mathematical metaphors. We did some kind of modeling for that, where the system then computes some generalizations of that in order to get a certain abstract representation of these things. And I think this is also something which goes into this direction, analogy making, concept blending, and metaphoric, giving something a metaphoric interpretation. Okay, now, having seen these examples, ranging from visual interpretation of visual input, certain reasoning tasks, certain developmental psychology learning tasks, so puzzles you can solve as a human being, interpreting poems and so on. Here are some classical types of reasoning and learning that are usually quite common in artificial intelligence. Here's a list of classical reasoning types. So if you do an AI class, so what you usually do is, I think, something like theorem proving. That would be something strongly related to deductions. You do something in perhaps somehow related to a learning, in structured domains, highly structured domain, the learning context, which is probably called induction, for example. Inductive logic programming would be something like this. Then there's this Sherlock Holmes idea, finding the right explanation for a certain result. This would be probably an abduction. Then there are, AI was famous for decades now in developing frameworks for so-called non-monotonic reasoning. So all these things like answer set programming or default logic or truth maintenance systems and I don't know what go into this, or circumscriptions, for example, go into this direction of modeling non-monotonic inferences. Then clearly very prominent now are all forms of frequency-based reasoning, as an example, Bayesian reasoning or some statistical regression methods or whatsoever. Vague and uncertain reasoning is also very prominent. Fuzzy logic is a topic here, for example. Then very special for a particular application domain is, for example, reasoning in ontologies with description logic, the very weak form of a very weak predicate logic, which is nearly propositional, and then contextual reasoning, and so on and so on. So we have quite a lot, actually. I don't claim that this is in any sense complete, but you have quite a lot of these things. And the same situation holds for learning issues, right? So if you look at learning here, some kind of a overview, which again is not considered to claim that this is in any sense complete. So we have the classical distinction into unsupervised, supervised learning and reinforcement learning, where usually reinforcement learning is somehow considered to be in between supervised and unsupervised learning. I added also analytic and inductive learning here. And then unsupervised learning is usually considered with clustering, whereas supervised learning is usually a classification problem. So you have classified examples, and then you get an unseen input, and then you have to say, well, to which class does this belong? And this is then a classification problem. And in reinforcement learning, you get a reward from the environment. We heard in the morning a little bit again about reinforcement learning, because these Monte Carlo the Monte Carlo techniques are somehow a little bit related to reinforcement learning, more or less. Also, clearly a reinforcement learning person would not explicitly say this reinforcement learning. And then you have some learning approaches, for example, for clustering neural networks, self-organizing maps or radial basis function networks, and for classification, classical case-based reasoning, classical decision tree learning, for example. The C45 is still benchmark algorithm for classification problems, k-nearest neighbor, and for reinforcement learning, Q learning, Markov decision processes, and clearly in all these degrees of freedom that exist, whether you have a deterministic environment or a stochastic environment, whether it's a fully observable Markov process or it's a not an only partially observable Markov decision process, and you have a POM-DP, and so on and so on. You have a whole variety of these things. The temporal difference learning was mentioned in the morning, actually. So the TD lambda on one of the slides in the morning. And then you have inductive learning and these kinds of stuff. So, and now comes the claim. So that are well-established techniques, well-established communities, good results. They can be applied to many interesting problems. These systems can sometimes, quite often, can learn things humans are not able to learn, by the way. So it's not that they are just some approximation of things humans can learn. They can learn much more. Because if you look in the benchmark problem database of machine learning, things try to learn anything from this data, right? It's completely impossible, but these systems can, right? So, and now my claim is, and to make it as provocative as possible, more or less all examples of human general intelligence shown before, so little pictures, the interpretation of the visual scenes, the interpretation of a poem, solving puzzles in the geometry domain, and so on and so on and so on, cannot be modeled by the mentioned classical reasoning and learning types. It's just impossible. Or at least I have no idea to do. Now, clearly, some people would strongly disagree here. I should say this. So, Jürgen Schmidhuber would probably not really agree on that. Markus Hutter, neither probably. But I want to make this claim, right? And here are some reasons for that. So, for example, the computation of the meaning of noun compounds requires usually a kind of a conceptual blending of two conceptual domains that are incompatible with each other. And this is hard to do, actually. Therefore, there are not many computational theories about this. The nested doll principle requires a form of analogical transfer of some structure to some completely incompatible domains, in a certain sense. The advertisement problem requires a form of creative analogy association. The learning of number concept requires a form of mathematical metaphors, as it was called by Lakoff and Nunez in their book. And the understanding of poems quite often contains many metaphors and analogies, and certain words do not stand for their literal meaning, but for something else. And all these things generate problems where natural language understanding people, for example, in this field, or certain learning people concerning if you want to model developmental psychological processes and stuff like that, have a hard time in a certain sense. Okay, so the claim is somehow all these good and well-developed theories are not really covering these examples and many more. And the claim is the modeling of the sketched human abilities should be modeled by cognitive mechanisms. And as two examples, I mentioned analogy making and concept blending, not because we think that are the only ones. I think there are many more, but because that is where we were concerned with in the last years, actually. So it's kind of a clearly subjective position. Okay, now let me give you some background about analogy making and some background about this framework heuristic-driven theory projection, and then we will look at some applications for them. Okay, analogy making and concept blending. First of all, some classical examples. What are analogies? The classical things you find are, for example, metaphors in natural language. So if you read something like gills are the lungs of fish, then everybody here has an immediate understanding what that means. Also, if you just look at the literal meaning, it claims that gills are lungs, which is just semantic nonsense, because gills are not lungs. But what is meant is not that gills are lungs, but that gills in fish have the same functions as lungs in mammals, although mammals is not mentioned here. And this is essentially the relation that is expressed by this. The same is true with things like electrons are the planets of the nucleus. Juliet is the sun. That's Shakespeare, by the way, Romeo and Juliet. I asked one time Ken Forbes, who is one of the leading figures in analogy making and generating analogy engines, what does Juliet is the sun meaning, actually? It's not so simple, right? He gave a relatively good answer to that. He just said, she's hot. That's a smart answer, actually. A classical other example is lawyers are sharks. Okay, and notice again, so just to make this point very clear, metaphors are necessarily semantic nonsense. They do not mean anything literally. So clearly lawyers are not sharks, and clearly Juliet cannot be the sun, right? Because the sun is a big ball, a sphere of some millions of degrees in the, and Juliet is a person.
It's funny how that metaphor doesn't quite work if you say Juliet is a sun.
Yeah. In a certain context, probably you could make some sense out of it. That's true. Yeah, but our egocentristic perspective on the world is just associated with the designated sun. Okay, here are some other examples. That is the reason why by the way, this analogy, why when I understood the name of this Airbus plane. This is called Beluga, this Airbus plane, on the left side. This is a plane, right, so it's flying. It's called Beluga, and on the right side you see some Beluga whales. And they look very similar, actually, just the form is relatively very similar. And then immediately I understood, oh, that's the reason why they gave it this name, right? Here's another example. If you think about the IT world is full of metaphors. Think about a computer mouse, or about viruses, for example, as in the IT world, for example, about drivers. Then the concept blends like, no, it only works in German, I think. For example, the German word for file, Datei, is a concept blend of Daten and Kartei, and then you make Datei out of it. So it blends two concepts to a new word, relatively interestingly. And all these things, there's a reason why a computer mouse is called mouse and not elephant. There's a reason for that. And the reason is because they have some structural properties with each other. And therefore they call it, and the same is true for viruses and all this kind of stuff. And then the classical domain is usually considered to be physics. So if you think about the physics domain and you want to explain a water flow model in such a pipe system with an electric circuit, you see many analogical relations. So for example, the pump on the left side corresponds to the battery in the electric circuit. The high pressure of the water corresponds to the high voltage on the electric circuit. The pipe system as a whole corresponds to the wires that connect the electric circuit. If you have a narrow of the tube here, then you can associate this with a resistance and a reservoir and ground and so on and so on. There's one web page where, from the University of Washington, I think, where they have many of these things actually. Very interesting analogies from physics. It's full of, very interactive. You can click on them and a lot of explanation is given there. And so I think physics, for example, is full of such things. Okay, now to give you some very rough idea what we do in our model in order to model such things. Usually analogy making is conceptualized as a process where you have to input entities, in our case theories, in other cases perhaps something else like graphs or some perhaps even some low-level input if you want. So for example, but in our case it's a source and a target, and it's a structured theory, usually represented in some kind of a many-sorted first-order language. And what the analogy engine is doing is, first of all, computing a generalization, an abstraction, which is based on a theory that goes back to the 70s, developed by Plotkin, Gordon Plotkin, still a member of the School of Informatics in the University of Edinburgh. And the idea is that you associate such rules, ground formulas, terms that have the lowest costs to be generalized. So for example, if you have here a relation between the mass of the sun and the mass of the planet of the sun is bigger than the mass of the planet, and here is something like the mass of the nucleus is bigger than the mass of the electron. You can generalize this to something like mass with a variable x. The constants are generalized to variables. Mass x is bigger than mass y. And the distance between sun and planet is bigger than 0, and the distance between electron and nucleus is bigger than 0. Can generalize this to distance x, y. Notice that this is an abstract representation of the original Rutherford scattering experiment, where he detected that electrons are not homogeneously distributed somewhere and arbitrarily close, for example, at the nucleus or even contained in it. But he detected in his experiments that there is a strict difference. They are strictly different of each other and heterogeneously distributed, the electrons and the nucleus. And this is an abstract representation that the distance is all the time bigger than 0. And there are some forces here. So for example, the sun, there's a gravity force between sun and planet, and there's a Coulomb force between nucleus and electron, and so on and so on. And then you can generate such generalizations. And this gives you, this anti-unification process gives you a abstract representation of the source and target input theories, and you code additionally the substitutions you need in order to get the source and the target domain back by applying the substitutions to the generalized theory. In principle, anti-unification works a little bit, it's just the inverse of unification you know from theorem proving. Right? In theorem proving, you have two terms, let's say, and you want to instantiate the variables in a way that the terms are not distinguishable from each other. That is unification. So fx and fy, and x and y are variables, and I instantiate x with, let's say, constant c, and y with constant c. I get fc, and so it's instantiating both terms via the substitution. And anti-unification is the inverse process. It introduces variables, replaces, so to speak, constants with variables x, y, z, and so on, in order to compute not a specification, but a generalization. Right? And then you get this romp-like structure. The idea is somehow the process is select terms and predicates formulas according to some heuristics. Start with the target side, order the facts and laws according to some heuristics, work through the list, take the first one, go to the source side, find a potential candidate for anti-unification, choose the one that generates minimal costs. This is mapped to the, this is written into the generalized theory. Then take the next formula or the term or whatever stands in your target theory. Search in the source to find, again, a candidate for anti-unification, write this again and work through this list. That's the idea of the algorithm. Everything is strongly heuristic, driven in a certain sense because, in principle, the ideas Occam's razor in a certain sense. So those things are preferred that generate very low costs, where substitution length, for example, are minimized. That's the idea or one of the major heuristics. And then you can get an interpretation on a semantic level. I will talk about this in one slide later, actually. Okay, now here's again some remarks concerning anti-unification. So anti-unification goes back to Plotkin, 1970. The task is to compute the least general generalizations of facts and rules of, in our case, originally Prolog programs. First order anti-unification was defined by Plotkin, 1970. First order anti-unification has really nice properties. So for example, it's guaranteed that generalizations exist in every case. It's guaranteed that there are at most finitely many, and it's guaranteed that there exists a unique least general or most specific generalization. So all nice properties. We actually deal with theories. We want also to generalize function symbols, relation symbols, in order to introduce second order variables for relations and functions, for example. And there, unfortunately, the bad story about this is that then some things are no longer true. So for example, that there are at most finitely many generalizations is no longer true, and that there exists a unique least general generalization is also not necessarily true. That produces some challenges, and here are four of them mentioned. So the first one is if you have something that generates potentially infinitely many possible generalizations that cannot be compared to each other, this is a problem, right, for a computational system. Then you have not only that you associate or anti-unify two formulas, but you have whole theories, and you need somehow a theory of anti-unification of theories. Then you probably have a learning process and a refinement process where you somehow get a trade-off of the coverage and the complexity of the computed generalizations. In particular, if you get new input for analogy making, this may be a further issue. And then clearly for analogy making, if you think about something like this, the natural question is what is the semantics of what you are computing here, right? This is a non-trivial thing. And in my opinion, there are still, for most analogy engines out there, there is no semantics for them. There is not really a semantics. So a model theoretic semantics for the symbolic approaches, at least, what that means. Now, I should make this a little bit short. Here's an answer to challenge one. We call this restricted higher order anti-unification, and the idea here is that you restrict the possible substitutions you can apply in order to compute your anti-unifications to four basic ones, we called it. They are called renaming, fixation, argument, insertion, and permutation. The formulas look ugly, I know, but the idea is relatively simple. Renaming is just if you have a variable for something, function variable or a relational variable or an individual variable, give it another. You can give it another name. Replace x with y. It's trivial. Fixation is just instantiation. If you have a variable of a function, for example, instantiated with a substitution as a function symbol. So from capital F t1 to tn, instantiated with f of t1 to t, and that is classical. That is what unification is about, actually, right? So that's a substitution that just specializes your variable with constants, or in this case, with a function or relational symbol. Argument insertion is a little bit tricky. This is the idea that sometimes you need to blow up your argument structure of a certain relation, for example, with dummies, or you want to shrink them. This is done with this complicated formula of argument insertion. And permutation is, for example, the problem if you have, for example, distance of relation, right? Or function, let's say. So a distance of x and y. And then usually what happens here is that distance xy is the same as distance yx, for example. So it's symmetric, right? And therefore, you need a possibility to make this permutation. You have only to change then, again, the function variable in order to not generate problems. In the general case, for example, you can do something like a smaller relation becomes a bigger relation, and then you just commute somehow from x smaller y. You can infer that y is bigger than x, for example, things like that. If you do that, you can prove that everything you can do in the first order case is covered. You can do every interesting case we know so far from a higher order case, and you can guarantee that there are at most finitely many possible anti-instances, and you can guarantee, so to speak, nice properties of these things, which is what you want. And then, actually, due to time restrictions, I skipped this a little bit. There is a kind of a resolution for challenge 2. With the theories, this is essentially just a commuting diagram here, where you specify somehow the a G, which is the most specific generalization of your input theories relative to your end unification process. And there is some story to say about learning process and analogy making that are, in our opinion, level-wise, actually, because you can on different levels, we were talking about this yesterday already, a little bit on different knowledge is somehow coded on different levels, and you want somehow to take care of this. So, for example, if you think about revolution processes in physics, there are many different levels of abstraction about things that circulate around something else. Some is a central mass system, for example, like a solar system. There's a central mass and some planets are revolving around, right? There are some revolving things where, for example, the mass is missing. That are so-called central force systems. Still it's revolving, but the mass is missing somehow, which is more abstract, the central force, because the force is also there in the central mass system. And there are some other things where you have, for example, just revolution processes that are kind of even physically relatively complicated. If you think about a merry-goes-around, for example, these are complicated revolution processes where forces are extremely difficult to describe physically. And these are abstraction processes. In physics, there are very, very abstract principles that are the abstract generalizations based on revisions through new domains. And there are very general principles that are at the top of physics. That is, for example, the preservation of energy, or things like that, right? That are way more general and more abstract, covering the whole field of physics in comparison to this domain-specific things. Okay, and this is my challenge 4 thing. Here there's a slide concerning the semantics of our model. This is a relatively, a little bit complicated because nobody knows category theory usually, and in particular this theory actually proposed by a computer scientist, Joseph Gauguin, who unfortunately died, I think, 2006 or 7. The theory of institutions. You have a common picture where you have on the signature level, sentence level, and models level certain morphisms and mappings between the things you are talking about. So in our case, because we introduce new symbols in the process, we need a mapping from a signature sigma to a signature sigma prime. And then if you can show that you are working in an institution automatically, so to speak, the sentences you can express with your signature can be transformed from sentence sigma to sentence sigma prime via a certain morphism in this category sentence. And contravariantly to what's going on in the sentence level, you have a morphism mod sigma that maps the models of sigma prime to the models of sigma in a contravariant way. Such that, for example, these well, this is actually a class of models. So one model taken out from this class is a model of sentence sigma if and only if the model sigma prime taken from this class is a model of the sentences of sigma prime. And this is in a contravariant version. So if I take a model here and a sentence here, then if I map this here, then this is a model of sentence sigma. If and only if I take sentence sigma, go to here, and then this original thing is a model of that. That's the contravariant relation. And this specifies the semantics of this level. Okay, now let me give you some application domains. So analogies, there is clearly more to say about this, and some of these things are somehow technical. But just to give, I think what I presented so far are just the essential ingredients of the whole thing, and to spell this out clearly is a little bit, would require more time. So analogies have been used to explain phenomena like, and here I give you only the list: creativity, learning of new concepts; development, learning of abstract concepts, for example, the number concept; problem solving, puzzles in the semantics of natural languages, and categorization of objects, and so on and so on. And I want now to talk about some potential future applications I found interesting, where I myself have not a clear idea how this can be used, but where I have the feeling or the impression that this should be the case. I skip my remarks to concept blending because due to time restrictions, and come to open issues for some applications. I want to talk about semantic web, smart control system, and text understanding. So let me start with the semantic web. And there was a Dagstuhl seminar very recently, some weeks ago, where precisely we were talking about these things, cognitive mechanisms, where it was cognitive approaches for the semantic web, but in principle it was about also analogies and some other cognitive mechanisms. And here is a query. So if you give a computer, a search engine, a query like how many cars of the type 530D Touring did BMW sell last year? If you do this, you don't get a reasonable answer, right? So you get, Google puts out many, many nice web pages that are almost all of them completely irrelevant. And actually I did this one time, and if you can read it, it's about everything, but not about the numbers of sold cars. So it's about where you can buy cars. There's a Wikipedia entries about BMW 5 Series. There's a test review. There again a sales thing. Steam cleaning engine bay, whatever that is. So I don't know. So you get a lot of, but there's nothing about how many cars are sold, right? And an advanced system should somehow deal with that. And then this is faced with many, many complicated problems. So the first thing has to do with natural language input, for example, because natural language input requires somehow an understanding of the question. And due to the fact that, as we saw, we usually don't say literally what we mean, but we say in a very strange things what we mean, the system has somehow to deal with that. A more fundamental problem is, and this is actually what I mentioned yesterday, that the semantic web people, or the knowledge collector somehow, they have a large knowledge base of elementary facts about the world. But in order to solve such problems, it's not sufficient to have just 30 billion RDF triples, because you cannot solve anything with 30 billion RDF triples. You need some intermediate levels where you can do some kind of real reasoning on that. And it's hard to get to this level, actually, right? And one problem here is to generate this, and our idea is currently, and this is pure speculation actually, perhaps it may be possible that you can automatically generate via analogy such generalizations between properties, between subdomains and subtheories in a certain sense. And then you get to a higher level where you have rules suddenly, not only these elementary RDF triplets. Okay, here's another one. I skipped this. Now, a further thing, smart control in a smart grid. This is something that grew out from some question from a company in Lower Saxony called it's the Kromschröder, and I think it was essentially about this thing here. So where's my mouse? Gone. About this thing here. This is a certain heating controller I think it's the Merlin 5046 or so, something like this. Some of the current models of this company. Usually they are hard to handle. Now, one task was, and this was done in a thesis actually very recently, to develop a design for such a controller as an iPhone app in order to with a mobile device control such a thing. The proposal of this student was this thing here, which is a really nice system. You can play around. It's really interactive. It's pure fun to do that. And then you can control your heating system. Now, clearly, the big picture is a different one, because the big picture is that in an intelligent household, you have a water meter, you have perhaps window sensors, perhaps you have door sensors as well, you have an optimized illumination, you have smart meters for your electricity, for example, with certain load profiles that specify when do you need electricity and when usually you do not need electricity, and so on. And you want somehow centrally control this with different devices, and you want somehow collect information about how people live in this house. So, for example, what is the schedule for the person living in the house? What is an optimization of the energy resources you have in order to get a comfortable living environment with generating a low amount of costs, but nevertheless the people living there are really happy and stuff like that. And then this should be controlled by different devices, for example, a laptop or a desktop or so, and clearly also, for example, from a mobile device like an iPhone or a smartphone in general, right? And now this generates many questions. The first one is clearly the HCI design here, how to design such an interface, what do you want to allow? And this is clearly a question that where, for example, strongly analogy issues come into place, because you have the classical things here, you have these interfaces here, you need somehow map these to each other, and they are usually not mappable so easily because they have a completely different structure, right? So, so one is the HCI design. Another one is clearly the knowledge collection or the knowledge acquisition. So if you want to learn a schedule of a certain person, you need to acquire knowledge. You need to acquire knowledge relative to many, many side parameters like outside temperature and where is the person at what time point and so on and so on. And this is a learning task that must somehow conceptualize in order to be reusable in the future and so on. And for such a scenario, for example, I could imagine that such cognitive principles could be one way to go, although this is clearly currently not an issue, but I could imagine that in the future you could make an issue out of that. And then clearly, if you want to make it really complicated, you could also think about a smart grid, for example, where you are not only a consumer of electricity, but you are also a producer of electricity because you have the solar cells on your roof or something like this. And then it's a complicated issue here to optimize some things. And as a last example, I want to mention the PhD thesis by Ekaterina Ovchinnikova, which was published 2012, relatively recently, the integration of world knowledge for natural language understanding. I exaggerate a little bit, but in principle what she built, what she did was, she has a kind of a Watson system in small as a PhD project. So it's not really a Watson system, but something very similar. It's a text recognition, text understanding system that can put into a text, and you get some and you can draw inferences out of that. It's a relatively complicated architecture, and it's massively knowledge-based. So she used ontologies, she used electronically available lexical databases, for example, like WordNet and FrameNet and things like that, in order to generate axioms. In total, this thing has nearly 1 million axioms where it's operating on and drawing inferences out of these 1 million axioms, which is quite a significant number for a knowledge-based system. In order to do that, she had to optimize several things. For example, this mini-Tacitus theorem prover is not designed for large knowledge bases, so she had to tune this thing significantly, and so on and so on. And she is now working in Los Angeles at the Information Sciences Institute, and when I visited her, these people now are also strongly interested in extending their system somehow with frameworks for analogy making, interpreting metaphors and stuff like that, because clearly that are crucial problems for all these non-literal meanings of text if you put text into such a system, right? And this is also, by the way, something where you can fool Watson, for example. If you give him not the right literal input, then the system has a problem, right? And I could imagine that in this whole business of text recognition, text understanding business, I think analogies and concept blending could play a role in the future. I think just about now noun compositor that can be relatively creatively used by humans. Here are my conclusions. This presentation argues for modeling certain problems in general intelligence with cognitive mechanisms. 2 examples of such cognitive mechanisms were proposed, analogy making and concept blending. I don't claim that are the only ones. It's just 2 proposals that for us seem relatively important. Heuristic-driven theory projection is an example of an analogy engine and an algorithmic framework that can compute analogies and concept blends. And besides the obvious applications I just sketched and gave an overview, my guess would be that several more domains are at least conceivable as an application domain, although clearly I do not have a clear idea how to use these things for these domains like semantic web or control systems and text understanding systems. There are some members of the AI group that were actually doing all this, so I didn't do anything. So their work, and I think that's it. Thank you very much.